you're ready, we can start. I think.
Okay, yeah.
Welcome back, everyone. Today we have Francesca, and she's going to tell us about generalized classes categories from n-Calabi-Yau triple.
Okay, so thanks, and thanks for inviting me to give this seminar. So yes, you just said I'm going to talk about generalized cluster categories that come from n-Calabi-Yau triples, and all the results I'm going to present today are from a paper that's been published in the Pacific Journal of Mathematics. So just as a general introduction, as I'm sure you're all aware, cluster theory starts from the definition of cluster algebras by Fomin and Zelevinsky in 2002. I won't really be talking about cluster algebras today, but I'll be talking about their categorifications. So the first categorification is the cluster category of a finite quiver with no loops or cycles by Marsh, Reinecke, Reiten, and Todorov in 2006, where the, well, I guess the easier case is when K is an algebraically closed field, Q is a finite quiver with no loops or cycles, and the cluster category is defined to be the orbit category obtained by taking the bounded derived category of mod K, mod KQ over tau inverse composed with sigma to Z, where, well, KQ is just the path algebra over Q. By small mod, we mean finitely generated modules. This is the bounded derived category. Tau is the Osnander-Reiten translation. So tau inverse is the inverse Osnander-Reiten translation. And sigma is just a suspension on our derived category. And by an orbit category, we mean one that where officially the objects of CQ are the same as the objects in this DB mod KQ. And the home spaces over CQ of, well, two objects X and Y are defined by taking direct sums over P in the integers of over DB mod KQ of X, and then, tau inverse composed with sigma to P of Y. So you can think of it as basically the objects in this CQ. So the objects in DQ that are in the same orbit of tau inverse sigma are in a way identified in this orbit category. And then this has been categorified, well, generalized this cluster category in several different ways. The first one I want to mention is the one by Iyama in 2009. And this was later, a couple of years later, generalized a bit further for higher cluster categories by Guo, but the setup is in a way the same. So if we start with Iyama's case, we start with a chain degli algebra with some extra properties that I'm not really listing, but for example, A is an homologically smooth, and A is has this property of being 3 Calabi-Yau bimodule. Then the generalized cluster category is a Verdier quotient. So she decided, well, she generalized she used Verdier quotients that are a more general concept than the one of orbit categories. So that's why, in a way, this is a further generalization. And it's the Verdier quotient obtained by taking the perfect derived category of A over dB of A, where the perfect derived category is the smallest triangulated subcategory of the derived category that contains A and it's stable under direct summands. And more generally, one can define a Verdier quotient by starting with a triangulated category T and then taking triangulated subcategory, for example, N. And then one can look at this quotient T over N, which is the Verdier quotient, and it's a triangulated category itself that comes with this universal quotient map, which we usually denote by Q. And basically the idea, well, you can think of it this way, or you can think of it as a localization where you invert all the morphisms in T that have cone in this subcategory N. And it's basically the triangulated category that annihilate, so basically just kills all the objects in this N. And then, so she also listed and proved the three main properties that make a cluster category basically a cluster category. So even in the original case, the things basically that made most of the results true about cluster categories are these three sets of properties. So our cluster category is a triangulated, home-finite, and n-Calabi-Yau category. It has two cluster tilting object A, and then it has this property that the endomorphism ring of A over the cluster category is isomorphic to H0 of A, so the cohomology at A. Where, just as I recall, n-Calabi-Yau means that D composed with hom over C of A of xy is isomorphic to hom of y sigma squared of x, where this D is the standard K duality, because we're working over a field K. And then also I just want to point out that this in this case, this is actually isomorphic to hom over the perfect derived category. So our original triangulated category we started with of A comma A. And the reason I want to point this out is because in the next generalization I will present, we actually won't have a chain dg algebra. So this third property will just skip this this thing in the middle, and we'll just have an equivalent property that says that the home spaces are isomorphic, basically. And as I mentioned before, then there is this further generalization by Guo for higher cluster categories, and where basically the setup is very similar and also the properties are very similar, but you use a bigger integer instead of 2. So basically here you'll have an n-Calabi-Yau property, and our C of A will have n cluster tilting object. And in the original set of properties, you will have the A, it will be an n+1 Calabi-Yau by module instead of being a 3 Calabi-Yau by module. So it's just a further generalization, but in a very similar setup. So the generalization I want to focus on is the one by Iyama and Yang from 2018. So the idea is that this generalized cluster category is a Verdier quotient still, but it comes from an n-Calabi-Yau triple, which I will define more carefully in a couple of slides. But the idea is basically, well, this is still a triangulated category with a triangulated subcategory. And then this M is a silting subcategory of T. And they also have some extra properties, which we will talk about in a moment. So they prove that these, well, the translations basically of these three main properties we were talking about hold. So you still have that this T over TFD, so this generalized cluster category is triangulated, it's unfinite, and n-1 Calabi-Yau. It has n-1 cluster tilting object M, so basically M plays the role of what A was playing before. And then the endomorphism space of M over this Verdier quotient is isomorphic to the endomorphism ring of M over T. So these were all already proven, as I was mentioning. My goal was to give a deeper understanding of this property, and the main thing I wanted to do was be able to describe home spaces over this T over TFD, which looked a bit mysterious to me to start with, by using home spaces or limits and colimits of home spaces of the ones in T that hopefully are a bit more easy to understand. And the way I did it, it was that by using some more classic homological tools, such as I was mentioning, direct and inverse systems, direct and inverse limits, and a gap theorem. So we can start with our setup and some definitions to see where we're working on. I'm pretty sure you're all quite familiar with the concept of torsion pairs and T structures, but just to, as a quick recall, a torsion pair on a triangulated category T is a pair of full subcategories such that X is left perp of Y is right perp of X, and X star Y is equal to T, where left perp of Y is the set of objects in T such that hom over T of these objects comma Y is 0. Similarly, right perp of X is the objects in T such that hom over T of anything in X comma T is 0. And then these star products are the objects in T such that there is a triangle in T of the form X to T to Y, where, well, the first object is in this subcategory X and the third one is in the subcategory Y. So basically this condition on X star Y being equal to T means that any object in T fits in such a triangle. And then T structure is a pair still of full subcategories of T, such that sigma inverse of the second half is inside the second half of this pair, and T less than or equal to 0, T bigger or equal to 1, where this is this shift, is a torsion pair. I think some people use a different notation for a T structure, but that's the one I'll be sticking to. And then an important fact is also that any shift of a T structure is also a T structure. So basically, if we define T less than or equal to M to be sigma to the minus M of T less than or equal to 0, and similarly for the other half, then we still have that this is a T structure if this was a T structure. So our setup starts with a fixed positive integer, which is at least 3, a field K, and then an n-Calabi-Yau triple. And so an n-Calabi-Yau triple consists of triangulated category T, which is k-linear, unfinite, and Schmidt, so nothing too crazy to ask. Triangulated subcategory TFD, such that TFD is relative n-Calabi-Yau, which means, so if this bifunctorial isomorphism was true for all of the objects in T, then we would say that T is n-Calabi-Yau. Instead, we're assuming something that's a bit weaker. So basically, we're assuming that we have a bifunctorial isomorphism of this form, but just, well, Y can be anything in T, but X has to be something in TFD. So it might be not true for some general object X in T, but it has to be true when X is in TFD. So in particular, if you had T n-Calabi-Yau, then it would be relative n-Calabi-Yau with respect to any triangulated subcategory. And then the last thing we need is that M is a silting subcategory with finitely many indecomposables. You could actually define n-Calabi-Yau triples without this finitely many indecomposable condition. And I think you would have to add maybe something slightly more in case you do that. But yeah, I'm focusing on this in this case. And so basically, a silting subcategory is one where T of M comma any positive shift of M is 0. So that would be pre-silting. And then we also assume that T is thick of M. So it's the smallest triangulated subcategory that contains M and is closed under direct summands. And then it also has a right adjacent T structure, T less than or equal to 0, T bigger or equal to 0, that consists of right perp of the negative shifts of M and right perp of the positive shifts of M. And this being, these having finitely many indecomposables also guarantees that in this case we also have another set basically of T structures with perp on the left instead of on the right. So, well, in general, when you have a T structure, you have truncation triangles. So also in this specific case. So for any integer P, but if we focus on positive ones, and any object X in T, well, we know that T less than or equal to minus P, T bigger or equal to minus P plus 1 is a torsion pair. And then by our definition of torsion pairs, that means that we can always get a triangle of this form. So where the first object is in the first half and the third object is in the second half of your torsion pair. But having a T structure also means that such a triangle is unique up to unique isomorphism. So we can call it the truncation triangle of X with respect to our T structure. And then, so we get these truncation triangles, but we also get morphisms between them. And well, between one and in a way the next one. So the two rows are two truncation triangles with respect to two different T structures. And then we have that, well, this first object is in T less than or equal to minus P. And if you think a bit about it, you can convince yourself that this lies inside T less than or equal to minus P plus 1. So the next basically truncation, well, T structure. And then, you know, we also know this is inside T bigger or equal to minus P plus 2. And well, we have that T less than or equal to minus P plus 1, comma T bigger or equal to minus P plus 2 is a torsion pair. So that means that there are no non-zero morphisms from anything in the first half to anything in the second half. So in particular, this composition is 0. And then by properties of triangulated categories, that means that you get a morphism psi of minus P such that this square commutes. And then you could also complete it to a morphism of triangles. So you also get this other one. We won't really care about the dashed morphism for the purpose of this talk. But yeah, I just wanted to point out that you actually get a morphism of triangles, not just this. And we will actually use this psi minus P to form our inverse system that we will use later on. But before doing that, I just wanted to point out what happens in the classic example, so the one on Amiot and Guo setup. So we have this chain DG algebra with some extra properties. And then if you take your triangulated category to be the perfect derived category, your triangulated subcategory to be the bounded derived category, and your silting subcategory to be add of A, then you get an n-Calabi-Yau triple. So you can recover their setup basically from this more general definition. And you can also say what the truncation triangles with respect to, well, one of these T structures are. And not very surprisingly, they are obtained by truncating the complex. So if you start with an X, then you can do the soft truncation to obtain your X less than or equal to minus P. And then you have this other truncation basically to get the other half, well, the other object in your truncation triangle. And this is actually an object in the bounded derived category. This comes from the fact that you start with a chain DG algebra. So your X, you can prove it's actually isomorphic to a complex that it's bounded on the right. So interrupting it somewhere on the left gives you a bounded complex. So as I was mentioning before, we want to work with an inverse system, and we obtain it using these maps between truncation triangles we were looking at before, so this size. And then for the very last one in your inverse system, you will get you will use this map for P equal to 0, so that you actually end in X. So we get this inverse system of objects, and then you can work for any objects in T, Y. We can apply T of blank comma Y. So this is just hom over T of blank comma Y. And this is our contravariant functor. And it gives you a, well, sorry, I didn't want to zoom. It gives us a direct system that also has a direct limit, because we're now over hom spaces over K, basically. So it flips all the arrows, because, yeah, we are using a contravariant functor. And this is a bit, I guess, of abuse of notation. By this dot, dot, dot going to the limit, I just mean that we get all these maps from the objects in your direct system to this limit, such that everything that needs to commute commutes. So we get this direct system, and well, we could do the same in our T over TFD. So we could view the triangles as triangles in this Verdier quotient, and we can look at the inverse system in T over TFD, and then we can also obtain a direct system with, well, over T over TFD instead of over T. And the interesting thing is that if we do that, then we get that everything in this direct system is an isomorphism. And the reason why we get this is because, well, if we look at our truncation triangles, the third object is always in this T bigger or equal to, well, minus P plus 1 in this case. And if we think a bit about it, we can, well, thanks to our setup, this is inside TFD, but then our Verdier quotient is basically, well, it's T over TFD, and it's a triangulated category, as I was mentioning before, that kills the objects in T, in TFD, so in this subcategory. So basically we have that X bigger or equal to minus P plus 1 is isomorphic over this Verdier quotient to 0. But then that means that this is an isomorphism over T over TFD. So X is isomorphic to any of these X less than or equal to minus P for P positive. And then, well, if we think about this a bit more, then we can see that that means that everything is an isomorphism in the corresponding direct system. And well, a direct system where everything is an isomorphism also gives you a limit that it's isomorphic to all of these objects involved. So we get this other direct system, and we can also build a commutative diagram between the two direct systems. So as the Verdier quotient comes with this quotient, with this universal quotient map, and we can use it to obtain these commutative squares, basically, between the Helm spaces over T and over T over TFD. And then, well, we can use the definition of direct limit, basically, to build this map such that everything still commutes. And the way we do it is, well, if we define MQ to be T of X less or equal to minus QY, then, well, for I less than J, we will get this commutative diagram to the limit, which just describes the first row of our system, basically, using this notation. And then, well, we can also obtain maps from these, what we're calling MQs, to this other limit by just composing our Q map with the map going to the limit, and you can do it at any step. And then thanks to commutativity, then everything commutes nicely. So if we call this L, we get this other commutative triangle. And then by the definition of direct limits, there must be a unique psi, such that this also commutes, and this is the psi we have in our diagram. And then, well, that'll be that's a different proof, of course, but we can use some properties of Verdier quotients and stuff to prove that this is actually a bijection. So we actually get an isomorphism between these two. And that's basically the main result in the paper I was mentioning before. So if we start with two objects in T, X and Y, then, well, we also have this extra thing. So for P big enough, the direct system over T, so the one that was the top row here, stabilizes, which means basically that the limit will be isomorphic to the Hom space of X less than or equal to minus P, comma Y for P big enough. And then that limit is also isomorphic to this Hom space over T over TFT. And the reason is just because, well, so we're saying that this is isomorphic to some T for P big enough to one of these Hom spaces over here. But then this is a bijection, and we also have that these two limits are isomorphic, but then this limit is also isomorphic to anything in the system. So also to this T over TFT of XY. So that's the main part of the theorem. And then the second part, I won't really talk too much about it, but I still thought it was important to include it. And it's just saying that, so basically you can compute these Hom spaces over your T over TFT, so your generalized cluster category, by using these limits and colimits over T of some of these objects that appear in the truncation triangles, or at least the limits of them. So that's the main idea. And as I was saying at the beginning, we want to use this, well, new results to reprove that this is actually, well, our T over TFT is actually a generalized cluster category. So we want to prove these three main sets of properties by using this new result. And yeah, I won't give full details on how to do this, but I still want to give an idea. So for the first property, we have that T over TFT is triangulated, and that's just because it's a Verdier quotient and the way we are constructing it. It's unfinite. This comes from our theorem. So we are assuming T is unfinite in the setup we started with. And then by our theorem, we know that T over TFT of between two objects X and Y is isomorphic to T of X less than or equal to minus Py for P big enough. But then since T is unfinite, this is a finite dimensional Hom space. And that means that also this is a finite dimensional Hom space. So our generalized cluster category is unfinite. And then for the n-1 Calabi-Yau property, yeah, I won't go too much into, well, into details of this, but it can be proved using the theorem and combining it with the relative n-Calabi-Yau property. So by doing that, you end up proving what you wanted, which is this D composed with T over TFT of XY is isomorphic to T over TFT of Y comma sigma to the n-1 of X. Before going to property 2, I'll mention property 3 first. So this fact that the endomorphism ring over T over TFT of M is isomorphic to the endomorphism ring of M over T. So if, well, in general, for this theorem, I said that this direct system stabilizes, but we can't really, well, we don't really have a rule of when that stabilizes. But if you look at a special case of Y, then you can actually say from one point on where it's actually a stable direct system. And the special case of Y is when Y is a shift of M. So if y is sigma j of m, then the system is stable from p equal to j minus n plus 2. And so that means, applying our theorem, that we have this isomorphism. So t over tfd of x comma sigma j of m is isomorphic to this t of x less than or equal to minus j plus n minus 2 comma sigma j of m. But then we could also, well, the even more special case of when j is 0 and x is also m gives us this first isomorphism. So just by putting x equal to m and j equal to 0 in this isomorphism up here. And then we also have that this m less than or equal to n minus 2 is inside t less than or equal to n minus 2. And we can prove that this is inside t less than or equal to 0. And then by uniqueness of truncation triangles, if you think about this for a moment, you can see that that means that m less than or equal to n minus 2 has to be isomorphic to m. And then, well, so these two have to be isomorphic, so we get this isomorphism here, which is what we wanted. So t over tfd of m comma m is isomorphic to this, which is property 3 up here. For the last property, which is property 2, we want to prove that this t over tfd has n minus 1 cluster tilting object m, and that means we have these two properties. Well, this is not the original definition of n minus 1 cluster tilting object, but it's equivalent. So to prove the first property, we can actually just apply again our theorem. And then for the second one, I'll just mention the results that one can use to prove it, but we need something else. So for the first half, we can take j between 1 and n minus 2. And then again, by using this special case of when y is equal to a shift of m, we know that we have this isomorphism, just exactly as before. It's just the same. And then for these choices of j, we know that minus j plus n minus 2 is positive. Well, it's at least 0, which means that t less than or equal to minus j plus n minus 2 has to be inside this t less than or equal to 0. And then again, by uniqueness of truncation triangles, we have that my m of less than or equal to minus j plus n minus 2 has to be isomorphic to m. This is over t. So we can substitute this with m, basically. Well, we get an isomorphism of this kind. And then as the last step, for this choice of j is always positive. Well, it's between 1 and n minus 2. And so since m is silting and j is positive, that means that this t of m comma sigma j of m is 0. And so combining this with this isomorphism, we end up saying that t over tfd of m comma sigma j of m is 0 for j between 1 and n minus 2, which is what we wanted for the first half of this property. And so the second half, so this the fact that t over tfd is isomorphic to this star product of m and shifts of m. So I won't really go into details on how you do it, but the theorem you can use to prove this is this gap theorem. If you start with an integer a and an object x in t, such that t of m comma sigma j of x is 0 for j between a and a plus n minus 2, then the truncation triangle, this truncation triangle, so the one with respect to t less than or equal to a minus 1, t bigger or equal to A as a torsion pair, splits. So that means that X is actually isomorphic to the direct sum of X less or equal to A minus 1 and X bigger or equal to A. Then, so you can prove this theorem, and then that can help proving the last part of the property we were missing. And I just wanted to point out that in the classic setup, so the one, well, the more classic setup, I guess, the one by Guo and Amio, this condition on the vanishing of these sum spaces becomes a condition on a vanishing condition on some degrees on the cohomology of X, because we have this T of M comma blank, which in that case is the Hom space over the perfect direct category of A comma blank is just H0 of blank. So basically this condition becomes a gap of n minus 1 consecutive degrees on the cohomology of X. So it makes sense that in that case X is isomorphic to the direct sum of these two truncations, basically. And yeah, so as I was mentioned before, one can use this gap theorem and its dual to prove the remaining point of property 3, where the dual of this gap theorem is holds basically thanks to this other set of T structures I haven't really talked about, but that are there. And then just I wanted to conclude by also mentioning that a very similar strategy can be used for the negative cluster category, which is another generalization. So I recopied the slide of our initial setup here, just because I wanted to point out what is different for the negative cluster category. So if we start with this setup, and then if we modify a bit, we get the setup we need for the negative cluster category. So basically, the main difference is that we have a negative Calabi-Yau triple instead of having a positive one. So we still have a triangulated category with the same conditions as before, and a triangulated subcategory. But now instead of imposing a relative n-Calabi-Yau property, we're imposing a relative minus n-Calabi-Yau property. So here we get this negative n. And one can do this even for a more general Serre functor. But yes, to get a negative Calabi-Yau, a negative cluster category, then you want to do it for a negative Calabi-Yau Serre functor. And then instead of having a silting subcategory, we have a simple-minded collection. So here we have T of M comma negative shifts of M being equal to 0 instead of the positive ones from before. We still have this condition on T, and we also have this extra condition on the dimension of the Hom spaces. And then instead of T structures, we have co-T structures. So we have this, left perp instead of the right perp. But most importantly, we have, here we have, in the first half, we have positive shifts, and in the second one, we have negative shifts instead of, the other way around. And these are co-T structures instead of being T structures, which are a bit more complicated to deal with, but we can do something similar. So basically the idea is that we can still build an inverse system and a direct system and play a bit with that, and we will get a very similar theorem to the one I was mentioning before. And we can use that to reprove that we have the relevant properties that make T over TFT a negative cluster category. And these negative cluster categories have been studied. I think they're a bit more recent concepts than the cluster category from before, and they've been studied by Coelho Simões, David Costello, Plug, and then Jean also proved quite a lot of these. I think he proved these properties of the negative cluster categories coming from these negative Calabi-Yau triples. So basically, these were already proved, but by generalizing, well, by reproving the theorem on the Hom spaces, basically I was talking about before, one can reprove these properties hold. So still that T over TFD is triangulated, it's unfinite, and has this negative Calabi-Yau property. And then M inside T over TFD is an M+1 simple-minded system, where these simple-minded systems, well, D simple-minded systems, if you want, are basically the corresponding idea to the cluster tilting subcategories in the positive case. So yeah, we can still, we still have this very similar theory for negative cluster categories, and the extra difficulty is that truncation triangles in Cauchy structures are not unique, while they are in T structures. So one has to be more careful when proving stuff here, but it's still possible basically, and it still works out. And I think I'll just stop here. Thank you.
Are there any questions? I will first ask people in the room so that other people in the room can type your question in the chat. So are there any questions from the in-person audience? So maybe I can quickly ask, specific motivation to define negative cluster categories, or it was just maybe like what happens if you replace?
Sorry, I couldn't hear properly, sorry.
Oh, sorry. Maybe grab a microphone.
Can you hear me well now? Okay.
Yes.
Yeah. So I asked, was there a specific motivation behind defining negative cluster categories?
I'm not too sure about what the original motivation was. I think I'm not sure if it's the way it was, but it just it looked like it made sense, I guess, because there was all this positive Calabi-Yau theory, and I guess it seemed plausible that something interesting could work for the negative case, but I'm not really sure what the original motivation was.
Thank you. Any other questions? Oh, Bethany.
Yes, I have a question. Can you hear me?
Yes.
Ah, great. Okay, that's good. Have you been able to use this technique to compute explicit homomorphism spaces, to compute examples, perhaps in geometric models and that sort of thing?
If I did it, or what was the question?
Yeah.
No, I actually didn't do it, but that would probably be the next step. That would be interesting. I just did it very general in this setup, but I didn't really look at examples. I didn't try to work out examples yet, but that would be a good start for something else, I guess. Okay,
thank you. Yes, I like the way the whole thing is really dual in the negative case. It really works out well.
Thank you.
So a follow-up question, maybe, Bethany, did you mean examples? So you have surfaces and finite arcs and so on, and then if you extend it to like infinitely many arcs and somehow has these direct limits. So do you mean generalize that combinatorics, and then maybe it will coincide with what is happening here abstractly?
It might give a technique for understanding those cases.
I see. Interesting. Thank you.
Interesting, yeah.
And do you know if you have a further if other silting objects become actually n+1 cluster tilting objects in this generalized case?
I don't.
In the sense that in the classical case, you usually have more than one two-cluster tilting object, right? I mean, and
Oh yeah.
and these are induced usually by other silting objects different from the one that you started. So if you pick another silting object in the
So you mean it for the silting objects, or for
right,
your M?
Yeah, so you start with another silting object in your so in another silting subcategory, which is say close enough to your M. Would this induce other cluster tilting objects in your generalized cluster category?
I actually didn't think of that.
Okay.
Maybe I can't recall if I read something about something similar to this or not, but maybe, I don't know.
Okay.
Possibly.
Okay. Yes.
Thank you. Are there any other questions in the room? Oh, chat. Okay, go ahead, Raquel. Comments on my question. Okay, from Raquel.
Sorry.
Oh yeah.
So one classical examples of negative Calabi-Yau come from stable modular categories of symmetric algebras and -1 Calabi-Yau. So it's kind of maybe this theory, the similarity with cluster tilting theory, can tell us something about this. Especially there's like this on the right hand conjecture in that setup. So I mean, it's not, maybe these techniques can be used there. So this is a motivation maybe for this thing.
Okay. Thanks.
Very interesting. Yeah, thank you, Raquel. And we have something in the chat.
Oh.
Oh, okay. So, so Bernard is asking if it's possible to have your slides.
Oh yeah, I think I uploaded them in that link I got, but yeah, I can just send them again if you.
Yeah, if you can send the link. Yeah, while you're doing it, we can thank Francesca again. Thank you very much.
Thank you. Shall I just put them on the chat, or you want?
Yeah, you can feel free to put them in the chat so people will have it. Okay, that's great. We got them.
Perfect.
Thank you very much.
Thank you.
Let me download them before it closes.
Yes, before closing the chat. But if you forget, then just email me. And I can send
yeah,
them.
sure.
Put them in the cap in the room as well.
Yeah, but so Whitney made a joke that can we put them in the chat in the room as well? I can give them, so I downloaded them. Okay, thank you very much, Francesca, for joining us today and for your beautiful talk.
Thank you for having me. Thanks.
Okay, see you everyone.